So we're in track 2, session 2A, object recognition, how to identify specific objects in images. And now we're going to come down from the kind of algorithmic conceptual approach level that Jan's really fascinating talk covered, and we're going to talk about implementation and how to build systems. And we're really fortunate to have as our next speaker Ken Lee from VanGogh Imaging. Ken is a serial entrepreneur who has launched multiple successful technology companies. And his current company, VanGogh Imaging, is focused on using vision, especially 3D vision, to solve real-world problems for industry. They say that one of the key characteristics of a successful entrepreneur is being willing to try things. And as you'll hear from Ken's talk, VanGogh has tried quite a few things in terms of how to implement 3D vision systems in the real world. And this is one of the things I really like about Ken's presentations, because his company is taking these fundamental technologies, the algorithms, the processors, the development tools, and taking them out into real-world situations and solving real problems for people. Ken's going to share with us some of VanGogh's recent experience implementing some of their algorithms and applications, specifically on FPGAs. So please help me welcome Ken Lee from VanGogh Imaging. Ken?
Hello? Okay, that's good. Thanks. Hi, as Jeff mentioned, I've been a serial entrepreneur for, I would say, a good 24 years. And part of that is a risk, willingness to take risk. And the biggest risk we took when we started VanGogh Imaging was that at the time, there were no low-cost sensors. So there's a good possibility that we may not have any of the 3D sensors that exist today. Fortunately, Microsoft stepped up and introduced their Kinect, and after that, we got a whole bunch of new 3D sensors coming out on the market, which is really driving this momentum, I believe, in this what Intel calls a perceptual computing momentum. So we're really excited about that. So I learned to program on a computer called Wang 2200. This is a long time ago, ancient history. So this is pre-Apple. Little known fact is that it was the first first complete desktop computer that you could buy. Had a cassette tape, had a processor, it's got a monitor all built in, plus a 8K of RAM. So, so a year after we got the computer in my high school, they upgraded to 32K, and everyone's like, wow, that's tons of memory. So, obviously the computers have come a long way, and it's much more powerful, and it's smaller and more capable. But to me, when I look at today's computer versus the computer I used 40 years ago, in terms of intelligence, what we call intelligence, it's just not quite there. It's really exciting that recently when we see things like Google Car, or the gesture recognition, or some of the augmented reality applications, I feel like it's finally starting to see the next wave, if you will, of this computing that can really make the machines more intelligent, if you will, than just use as a tool. So thank you today for giving me the opportunity to introduce VanGogh, and hopefully I'll talk about our experience on our implementation of the object recognition. Our company is a few years old. We actually worked on a couple of real-life 3D computer vision projects. One in agriculture, of all things, that uses a 3D sensor to weight animals' weight, livestock weight. So we had some interesting experiences. That's where we got a lot of great experience on how to really take these algorithms and apply it in a real-world situation. It's one thing to have algorithms that are really good in the lab, But you take it out in the real world, it's a completely different story. So I'm sure as many of you know. So we came out with this concept called Starry Night. So Starry Night is, we call it middleware, but it's more than just a library. It's really a computer vision subsystem. It's based on our experience with our real life application development, is that most libraries today, OpenCV or PCL, they're very excellent libraries, and we do use some of that as well. But it's very difficult to use for most application engineers. If you're an application engineer in automotive or security or whatever, you want to implement something in visual, it's very difficult to do because let's say you take an object recognition piece right here. That alone requires maybe 10 different functions from these libraries. You got to put it all together, you got to test it, and so on, and get it to work. And that's the point with Starry Night, is to not only handle the real life situation, which means it needs all the pieces need to be really robust. It needs to run on kind of the resources that are not on a platform that doesn't have a lot of resources. Like a mobile device or embedded devices. So we have this, we developed this function, which will be out next month on the, we're putting that on the AvNet embedded software store as kind of a free beta version. It has 4 different functions within the system, if you will, subsystem. First is a capture, which we use SLAM. SLAM is a technique used a lot in robotics, which tells you where the camera location is relative to the scene, for example. And then, so when you capture the scene, and then you recognize objects, and then you can convert that to mesh right away, or we have our own unique, what we call shape-based registration technique, which is unique to us, which we developed to make it more tolerant to the real world situation, and also make it more robust. And then we have an analysis tool that tells you about the object. So function query, so this is a Unity plugin. It's available on Unity plugin for the mobile devices. So function query would be like, where's the object? And it will tell you where the object is. And then say, which way is the object facing? So it tells you where the object is facing. And how big is the object? Say, oh, it's 30 centimeters. What is the volume of the object? So those are the function calls you make. So pretty much any application engineer can use this without becoming a quote-unquote expert in computer vision. So that's the what I like to highlight as a core benefit of Starry Night. Just briefly about the shape-based registration. This is our unique approach to 3D modeling. Typically, when you do modeling, you take a whole bunch of scans, you stitch them together, and you come up with a 3D model. So in the real world, it's difficult because you only have sometimes one scan, or just a few scans, 3, 4 scans or whatever. Then you got to take that, and then you stitch it, but then you got a bunch of holes in there, and it's, you got noise, so you got to smooth them, and so on. So we came out with this technique called shape-based, which is you start with kind of a reference model, the middle image, if you will. So it kind of looks like your head, let's say, but it doesn't have to be your head. And then you take the input scan, and you deform the reference model into a fully formed 3D model. So you start with a fully formed 3D model in the beginning, you use the scan points to modify it, you still end up with a fully formed 3D model. Great thing about it is that you have 100% knowledge of the data structure of that 3D model. Basically, the relationship at every point to all the other points in that 3D model. So it makes it very easy to do pretty much anything, feature detection or measurement or what have you. So, but in any case, we're here to talk about object recognition algorithm. So in terms of the recognizing object in the scene, it's very difficult. As you can see, there's, the object can be in all kinds of different orientation. It could be occlusions. And on top of that, you have very limited resources. And you want to make it as low cost as possible, obviously. So we needed a very efficient algorithm. So we looked at a number of different algorithms, including texture-based. But problem with the texture-based is there's a lot of lighting issues. Color of the object is not always the same. Machine learning is great, but it does require a lot of training. So, these techniques don't give you necessarily you could, but it's more difficult to give you the orientation, exactly which way is the object facing. So then we start looking at 3D methods, and we try one of them, but most of these algorithms are fairly slow. Another big problem is if you want to look for multiple objects in a scene, so let's say you want to find 2 objects, generally it takes twice as long to find 2 objects versus a single object. So, just stepping back before I get into what we did is this general concept of the object recognition is, once again at the top, you have kind of this, you find the object descriptor. So object descriptor could be a number of things, as you already been introduced to, but in our case, we use distance and normal functions. So, distance between points. So you got all these points in a 3D space. So it's a combination of distance and normals. So what is normal is the surface normal, which is, which way is the arrow pointing. So my surface normal of my face, for example, will be heading this way. If I look up, then the surface normal of the face will be pointing up. So, then you use that to kind of create what we call an object descriptor. And then in the scene, as you capture the scene, you do the same thing. You kind of randomly sample different points in the scene, and then you compare the descriptor. So if there's a match, it's like, oh, okay, there's a match. So now we got a match, then you use a match criteria to see if there's a really good match. Okay, well, there's a really good match. Then next step is you kind of fine-tune the orientation, make sure that you got the exact right orientation. So at the end, you get both the location and the exact orientation, what we call transpose of the object. The workflow is that the models are pre-processed. So it's time-consuming to generate this big model descriptor. So, and you don't have to do this real time. So you pre-process the model, you come up with the descriptor. Then as the scans come in from a scanner in kind of so many frames per second, that first we remove the flat surface because flat surface doesn't have a lot of features. So we like to do that to kind of remove more of the points. And then we downsample a little bit to make the number of points more reasonable. Then we randomly sample them. A good number to use in a scene sampling is usually about 500. So in our case, we do like anywhere from 100 to 500 pair of points. So and then you do the comparison. So the drilling down further, so going back to the model descriptor. So model descriptor is a collection of, it's a hash table made up of these factors. The hash table, as I'm sure you recall, some of you recall, is the very fast lookup table. Okay, so you have this hash function, you put the input and tells you, oh yeah, go look at this row to find the value. So way we generate this hash table is like in the bear example, we grab 2 points. So we look at all the points in the bear example, and we look at all the pairs that are exactly 5 centimeters apart. So there's a bunch of points that are 5 centimeters apart in the 3D space within the object, right? So you got that. Then you also look at you grab the surface normals of those 2 points. Then now you got 2 normals plus these 2 points, x, y, z's. You convert them into 3 angles, which is angle of the normal of the one point respect to the other point, angle of the normal, angle from the normal of the other point to the first point, and then the angle of the plane in between the points. So from there, so that's for the one point pair, right? So then you kind of assemble this table where because you're going to have some pair of points that have kind of similar descriptor, similar the three angles. So you create this hash table and that becomes your model descriptor. Then in real time, as you grab the scene, for example, the scene we use had about 15,000 points. Then we sample the point pair in the scene. So we go to the scene and we grab a point pair, right? So then they're using the ransack. It's also 5 centimeters apart. Then we generate the key. We do the same process, right? The 2 normals plus and it's the same distance, obviously. And then you throw that into a hash function and you go to the lookup table. You look at the points of the points that are available for that key on the lookup table. And now I go, okay, so these points in the scene match these 2 points in the object, we think. So we take this object, we try to fit it into the scene. And you look at the match criteria. We go, okay, that's a good match. Or we try to throw that on there, it's like, that's a bad match. And then we move on. And if the match criteria works, then we use ICP to kind of refine the position. So the nice thing about this approach is there are several nice things. Is that one is we can really parallelize this whole process very easily, so we can get the performance we need. It's a hash table, so it's a very fast lookup table. Another characteristic is because we only have one hash table, if you do 2 objects, it's no longer twice. It doesn't take twice as long. It takes maybe about 20–30% longer. So it's a very efficient algorithm, and we've been pretty impressed with how well it worked. Okay. So result is that we are able to now find the object in the busy scene. So in terms of performance, it's fairly reliable. And these are numbers from about 2 weeks ago. So we improved this since then. So you get some number of false positives. So there's the example of a false positive. It's not, we found it in the wrong place. In the clean scene, I mean, it's pretty much works, almost 100%. Noisy environment, we got it down now to about 10% or so. So I think we're really making good progress just within the last 2 weeks. In the success ratio wise, it's also dependent on the orientation. So when the bear was sideways, it didn't do as well because there aren't as many points on the side. We got that down to up to about 80% now. So it's just one of those things that we just need to continue to improve. So on the mobile device, you will see a demo out there. We got it running actually about 2 frames per second on a mobile device, on a Samsung phone. And then on the in terms of for the embedded application, we've been working on porting our Starry Night onto the Xilinx Zinc. And we like the Zinc processor because Zinc is a SoC, system on a chip. It has 2 arms and a 2 ARM core and a FPGA. So FPGA is wonderful because we can make these the complex functions and throw it on there. It runs in 2 clock cycles. And on top of that, we can have a whole bunch of those processing units. On top of that, then when you're doing, let's say, capture, you use FPGA for capture. And then when you're done, you're going to use it. You can load the object recognition algorithm on there and use it just for object recognition. So it gives you a lot of flexibility. And also, most embedded application requires some type of hardware controls anyway. So we think it's a perfect platform for most embedded applications. We implemented this entire function on the Zinc, amazingly, just using C++, which amazed me because I used the FPGA 30 years ago and I hated it. So, but now it's really, I mean, it was a really good experience. And there's obviously a lot of work to be done. Currently, we are only able to get a portion of the algorithm optimized using our latest algorithm. So, but I think within about 2-3 weeks, we'll also have a much faster performance. Generally, the Zinc 7020 runs in general, about twice as fast as the ARM processor. 7045 will run, we estimate, somewhere around 5 to 7 times what you can do on the ARM processor for certain functions. So lessons learned is that number one, it's very difficult, but secondly, it's a lot of fun. And there's a lot of improvements to be made, both on the ARM implementation as well as on the FPGA core. One thing that we did learn is that algorithm that works on one platform, ARM, let's say, it doesn't necessarily translate directly optimally into other processing cores, but generally, please stop by the booth and check out the demo. So that's it.
Thank you very much, Ken.